Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. The topic for today's presentation is case study on optimization of distillation process. The case study deals with an economic analysis of converting conventional propylene propane splitter to MVR heat pump system. In the part 2 of the optimization of distillation process, we deliberated on the most commonly used heat integration technologies. In my closing talk, I promised you that I will be back with a case study on heat integrated technologies in the next video. You are with me on the topic today. You will strengthen your understanding of the heat pump system and learn through this case study how economically the MVR heat pump system is superior to the conventional system and what improvement in efficiency can be achieved in the heat pump system over the conventional system. We will now walk you through the case study on heat pump system implemented in a petrochemical plant. Case study description. A petrochemical plant has installed a olefin separation unit which has a propane-propylene splitter for production of polymer grade propylene. The conventional propane-propylene splitter is energy intensive. After a detailed techno-economic analysis, the company decided to go for MVR heat pump system instead of conventional cryogenic distillation system at the design stage itself. The company realized substantial saving in cost upon implementation of MVR HP system. In this case study, we will evaluate the existing conventional system and the MVR system and understand the benefits realized. This figure illustrates the conventional propane-propylene splitter operated under cryogenic conditions. The reboiler is driven by steam. The cryogenic condition needs a refrigerant for condensing the overhead vapor at sub-atmospheric temperature. We will use a process simulation package to get the mass and energy balance for the propane-propylene splitter column. Shown here is the operation flow sheet of the propylene-propane splitter for the simulation. With reference to the above operation flow sheet for the column, the system data are: column is a tray column, number of stages 250, feed stage 149, condenser type total condenser, reboiler is partial liquid. Now select the thermodynamic package for the simulation. K value, equation of state model, Peng-Robinson. Here you can see the feed stream specification for the flow sheet. There are several compounds present in the feed stream apart from the main components propane and propylene. Though they are present in very low level of concentration, it is extremely important that they get separated and do not find their way into the distillate product. The feed stream main components and compositions are propane 55%, propylene 43%. Next, you define the specification for the column simulation. The operating data such as top pressure, column pressure drop or bottom pressure, and the feed temperature and pressures are specified. Other column specifications required for solving the flow sheet are distillate and bottom product specifications. The data are column top and bottom pressure 5.7 and 6.7 bar respectively, feed pressure 6.46 bar, feed temperature 7.3 degrees centigrade, distillate purity 99.5%, propylene slippage at the bottom 3%. Having specified the feed and the column specifications, you can solve the problem now. The column converges without any issue. This table shows the stream data for the columns obtained from the process simulation results. The feed, distillate and bottom products flows and the stream-wise components flow can be viewed here. This is the mass and energy balance of the conventional distillation process obtained by simulation. This data is a vapor liquid traffic through the column extracted from the simulation result. The column top and bottom temperatures are primarily the boiling points of the propylene and propane system. This data along with column top vapor data are required for designing MVR heat pump. The K-value profile is shown here. At stage 1, the relative volatility alpha is 1.2. At the bottom stage, that is stage 250, the value of alpha is 1.19. The very low relative volatility requires very high reflux. As we discussed a while ago, due to close boiling point and low relative volatility, large number of theoretical stages are required. Take a look at the McCabe diagram for the propylene propane system given here to understand it better. From the liquid composition profile across the stages, we can determine the key ratio. The optimum feed location is 1, where the key ratio in the feed matches with the key ratio in the stage. We have the feed specification, so we can calculate the key ratio of the feed. The liquid composition profile across the stages given in the table here. This data is derived from the simulation results. In the feed stage 149, the concentration of propylene is 0.436 and that of propane is 0.558. The calculated key ratio in the feed is 0.785 and the feed plate is 0.781. This indicates the feed plate location is optimum. The reflux ratio for the conventional splitter is 11.37. That is the reason why high boil-up ratio is needed. The boil-up ratio for the present case is 8.83. Hence, to split the given feed of propylene and propane, roughly 10 to 11 times the product rates have to be processed through the column. Extremely energy intensive. The heat duty of the reboiler is 75.27 megawatt and the heat duty of the condenser is 70.28 megawatt. As we discussed above, the condensing temperature of the overhead vapor is minus 1.2 degrees centigrade. Hence, a refrigerant is needed. The choice of refrigerant include various options. Some of the commonly used refrigerant include ethylene, propylene, ammonia, etc. depending on the temperature. The existing refrigeration system in the plant should be given the preference since it will be part of the integrated system as well as being economical. We have now made the Mosen energy balance and determined the energy requirement of the conventional cryogenic propane propylene splitter. We have also checked and confirmed the feed location by determining the key ratios. We will now move on to determine the parameters for design of the MVR heat pump system. I presume that you have gone through and learned the MVR heat pump system in the part 2 of the course on optimization of distillation process. If you haven't, I recommend you go through the video. I will not be repeating it again here. Illustrated here are the two systems. We are going to design the MVR system and make an economic analysis of the new system to determine whether it will be a wise investment decision. The first step is to determine delta TB and delta T lift. Delta T lift is obtained from the boiling point difference between the light key and heavy key, which in this case study is 13.71 degrees centigrade. We can now determine the delta of T lift, which will be 20 degrees centigrade higher than delta TB. So delta TB works out to 33.71 degrees centigrade as shown here. Since the vapor is propylene, the saturation pressure of the propylene vapor at 33.17 degrees centigrade is 11.7 bar G. To take into account the pressure drop in the downstream system, including reboiler, we shall select a compressor with discharge pressure of 12.4 bar G. The suction pressure of the compressor is the pressure at the top of the column, which in this case is 5.4 bar G. The pressure ratio for the compressor, which is the ratio of discharge pressure to the suction pressure, is 2.29. The pressure ratio of a single stage centrifugal compressor used in the petrochemical industry is limited to less than 1.5. Hence, a single stage compressor is not adequate. Hence, a two-stage compressor is selected. The total brake horsepower required for the compressor is the sum of the power required for the two individual stages. For the first stage, the power required is 6.57 megawatt, and for the second stage, the power required is 6.43 megawatt. So the total power required is 13 megawatt. Here you have to note another important point in the study. The vapor load to the compressor is higher than the actual vapor generated from the stage 1 of the distillation column. The additional vapor comes from the flashing of propylene liquid across the reflux flow control valve. The flash vapor quantity becomes part of the mass balance. This is the MVR HP scheme for the propane-propylene splitter. The vapor from the column top is compressed to 13.4 bar pressure and is condensed in the reboiler at 32.6 degrees centigrade. The condensed subcooled propylene liquid flows to the reflux drum. From the reflux drum, the liquid is further subcooled by propylene refrigerant to reduce vaporization due to letdown across the flow control valve. The remaining liquid from the reflux drum is withdrawn as product propylene under level control. Here you can see the vapor heat load analysis of the MVR heat pump system. Heat load of the vapor to be removed is 75.28 megawatt. Power to the compressor or work done by the compressor is 13.65 megawatt. Heat consumed by the reboiler 75.27 megawatt. No steam is used by reboiling. You have completely eliminated the steam requirement for the reboiler. In this analysis, I did not include the refrigerant load for the condenser in the conventional cryogenic distillation system because the load is part of the common refrigeration network of the entire plant. You need to have full data to include this analysis. This table shows the energy balance for MVR heat pump system in our case study. Heat to be removed to condense the overhead vapor from the column minus 75.28 megawatt. Compressor work done minus 13 megawatt. Heat to be added in the reboiler plus 75.27 megawatt. Flash vapor generated due to reduction in pressure across the flow control valve plus 12.79 megawatt. Work equivalent of head required for the reflux 0.48 megawatt. Now you can calculate the energy saving for the MVR heat pump system. The compressor power is 13.0 megawatt. Steam utility eliminated for the reboiler heat duty is 75.27 megawatt. The net heat saving is 62.27 megawatt. The MVR heat pump assisted distillation propane splitter uses only 1/6 of the energy compared to the conventional steam heated distillation system. Here I present the thermodynamic efficiency calculation. For the conventional cryogenic distillation system, the calculated efficiency is 2.47%. It was expected because of the close boiling point between propylene and propane and high reflux requirement. The MVR heat pump system thermodynamic efficiency is 14.35%. There is a huge improvement in the thermodynamic efficiency. This case study highlights the enormous potential for energy saving in distillation process through heat integration technologies. You will find more such innovative technologies being implemented in the distillation process in the days to come with enormous amount of energy saving. Subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation on the case study on heat integrated technologies. Hope this presentation with narration and animation was useful. Share with your friends and colleagues to reach out to a large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Thank you for watching.